5.4 example 5. Use a calculator to find how many times the graph of y equals x squared minus 3 plus the sine of 2x minus 1 changes concavity in the interval from 0 to 2 pi. So what I did on this problem is I went ahead and found the first derivative and the second derivative. So if I was finding that first derivative, 2x, the derivative of negative 3 is 0, and then the derivative of sine 2x minus 1 is going to be 2 cosine 2x minus 1, using the chain rule. And then I found the second derivative. So 2, I was going to say plus, but then I realized that the derivative of cosine is negative sine. So minus, and then I would multiply by 2 again, so 4 sine of 2x minus 1. All right. So now, it says use your calculator. So what we're going to do is we're going to look to see how many times this is 0. Because remember, when we're finding our critical points here, we would be looking at this function and how many times it is 0. I, of course, on my paper did it using algebra, but it is kind of a lengthy problem using algebra. So what I'm going to do is I'm going to switch over to my Desmos calculator on here. Hopefully you can still see this when I bring it up. And I have put in red is our original function, and in blue is the first derivative, and in green is our second derivative. And so if we focus on the green, and remember we're talking about from 0 to 2 pi, which is 6.28. So we're talking, about from about here to here. You're going to see that it goes from positive to negative, okay? And then it goes negative to positive, then positive to negative, negative to positive, and then it stays positive till 2 pi, till 2 pi comes. It'll keep going, but we want to know how many times it changes concavity. Well, each time, like these are going to be your critical points where this green function is 0. And so if it changes from positive to negative or negative to positive, that means concavity is changing. Remember, the second derivative, when it changes, that's a point of inflection. So I can see it changing 1, 2, 3, 4 times between 0 and 2 pi. And we could figure out what those points are, but it just says how many. And so if we go back to our notes here, we would say that y changes concavity 4 times in 0 to pi interval, okay? Because I knew that and it was hard to see. I don't know if you paid attention to your original function when we were over there on Desmos, but when you look at this red function, it's hard to see how many times it's changing concavity. So luckily we were able to pull up that derivative and look at that. All right, our next one, use a calculator. Using a calculator, find the values of x at which the graph of y equals e to the x times x squared changes concavity. So again, we're going to look at the first derivative, and I have to use the product rule. First times the derivative of the second plus second times the derivative of the first. So this is going to be 2x times e to the x plus x squared times e to the x. And if you were trying to solve this for, you know, for 0, I probably would factor that e to the x out. E to the x would never be 0, and you could just set that equal to 0. But we need to find the second derivative now, so I'm gonna use this one. So I've got the first times the derivative of the second plus the second times the derivative of the first. And then for the next one, I've got first times the derivative of the second plus second times the derivative of the first. So my second derivative, I've got 2x e to the x here. I've also got 2x e to the x here. So that's going to be 4x e to the x plus x squared e to the x plus 2 e to the x. And if I factored an e to the x out, I probably would put my x squared first, plus 4x plus 2. And I could put that in my calculator and look at how many times. So I'm going to go back over to my Desmos calculator again, only this time we're going to go to example 6. I had already put it in, and you can see that the green one is my second derivative. I already put those functions in, and you can see that it changes once here, and it changes once about right here. Okay, so you can kind of see that this one is going to change concavity 2 times. Okay, and we're talking about the original function. So look how that coincides here with the change from going from concave down to concave up. And look, it goes from negative to positive. Your second derivative does. But we're talking about the red function. And then the same thing happens over here, where it goes from being concave down, about right there, where the 0 is, to concave up. So 2 times is going to be my answer for this one. So I'm going to say that y changes concavity 2 times because y double prime goes from negative to positive and positive to negative twice. And there's better ways to say that, but you know, and up here you could have said because the sign of y double prime changes 4 times in the interval. Okay. All right, so now using the second derivative to find extrema of a function. Similarly, the second derivative is the first derivative of f prime of x. So the same relationship that exists between f of x and f prime of x must also exist between f prime of x and f double prime of x. We can use the second derivative test as an alternate method for locating relative extrema. So if x equals c is a critical number of f of x, then f prime of c equals 0 or f prime of c does not exist. This makes x equals c a possible maximum or minimum value of the function f of x. So what happens when we have a positive second derivative? Our original function is concave up. When we have a positive second derivative, our first derivative is increasing. When we have a negative second derivative, our original function is concave down. And when our derivative is negative, that means it's decreasing function. When we have neither for our second derivative, we have a possible point of inflection. And then for f prime, we have a possible relative max or min. Okay? So now, example number 7 is use the second derivative test to find the relative extrema for each function and justify. So what ends up happening is the second derivative test, you have to know the first derivative critical points to use the second derivative test. So what we're going to do, even though we're using the second derivative test, we first have to take the first derivative and set it equal to 0 because we need to know what those critical points are. And so x equals 0 and x equals 6 are our critical numbers, which, you know, if we found the corresponding y value, they'd be technically critical points. And here's where we make a little chart. We've got x equals 0 and x equals 6. Our original function, we could find g of 0, and of course, that one's easy, it's -5. If I wanted to find g of 6, I would put it in my calculator with, of course, my original function here, and I would get -437. So we've got -5, -437. So now, my second derivative, we're going to have 12x squared minus 48x, set it equal to 0, 12x is common, x minus 4 is left, x equals 0, x equals 4 are my critical points or my critical numbers, okay? My g double prime of 0 is 0. My g double prime of 6 is 144. Why did I use 0 and 6? Well, because our second derivative test, when we, what we're doing is we're taking and we're saying if our second derivative, so up here I'm going to fill this in, sorry, this one is 0, so that's inconclusive. This one is positive though, okay? So this is our conclusion based on our second derivative test. This tells us that number 1, we have a local min that occurs at x equals 6 and is -437 because g double prime at 6 is greater than 0. So that means that g is concave up at 6. Well, if it's concave up at 6, doesn't that mean that you would have a min here at the concave up point for your first, the critical point for your first derivative? If the second derivative at 6 is positive, that's concave up, so you knew you had a minimum. And then the second thing, we have no conclusion on extrema. For x equals 0, since g double prime of 0 equals 0. So if it's negative, that means you have a local max. If the second derivative is negative at the critical point of your first derivative, because you're trying to, instead of using the first derivative test, you're trying to decide, is this a max or a min here, right? So that's what we're trying to decide. And instead of using the sign chart, we're saying, hey, we're going to take the first derivative, find our critical points. We're going to decide whether it's a max or a min by taking the second derivative and looking at what the sign of the second derivative is at the first derivative's critical points. Okay? So I found the critical points or critical numbers for the second derivative, okay? But actually, what we're doing is we're taking the first derivative's critical numbers and putting them into the second derivative. If you get positive, you've got a min there, okay? So positive means concave up, that's a min at 6. If this would have been negative, that would have been concave down, and this would have been meant that we had a maximum. But when it equals 0, it is inconclusive, and you would have to go back to the first derivative test to find out what's going on. So you'd go back and you'd say, okay, well, here I am back to my first derivative test. I'm looking at g prime. You'd put a -1 in, you get positive times negative, that's negative. You put a +1 in, that's positive times negative, that's negative. So you can see here that there is not a max or a min at 0, okay? Because it does not change from positive to negative or negative to positive. It stays the same. So that means that you've probably got like a flattening off point, but it still is negative, negative derivatives after that on either side of it. All right, so let's look at part B. We're going to take the derivative. So this is going to be 1/2 minus cosine x. I went ahead and set it equal to 0 because remember you're trying to basically find your critical points and then use the second derivative to see whether they're maxes or mins, okay? So where is cosine positive? All students take calculus. They're all positive here, and cosine's positive in the fourth. And so that means 1/2. This would be square root of 3. This one's going to be negative square root of 3. 60-degree angle is pi over 3. And ooh, we got to be careful here because I just noticed that we're talking about from -2 pi all the way to pi. So think about where -2 pi would be. If I was going this way, the first thing I would hit is negative pi over 2. Then I would hit negative pi. Then I would hit negative 3 pi over 2. Then I would hit negative 2 pi. Okay? So I have to look at it for all of those values from negative 2 pi all the way around and then back again. So basically from negative 2 pi we're going to be going all the way around, and then we're going to go one more time to positive pi. Okay, so that gives us kind of a lot of things going on, although it's only happening in these two quadrants. But we have to make sure, it's almost like if you had a number line here and you were going negative 2 pi, and we said negative 3 pi over 2, negative pi over 2, there's my 0, there's my pi over 2, there's my pi. So you're talking about from negative 2 pi all the way to pi. And so our critical points are going to be pi over 3. That is one of them because that's in the first quadrant. Okay, so that definitely is one of them. And also negative pi over 3. That's the fourth quadrant. Okay, so that would be when you're first starting out, that would be your first one that you would see. Okay, then you'd keep going around. This one actually is negative. If you went all the way around, negative 2 pi is negative 6 pi over 3, so it's 1 pi over 3 shy of that. So that is negative 5 pi over 3. So you've got negative 5 pi over 3, negative pi over 3, you've got pi over 3, but then you don't hit the fourth quadrant again. So you really only have these 3 critical points. And so these are, and I'm just going to list them as the smallest to largest. So negative 5 pi over 3, negative pi over 3, and then positive pi over 3. And then I take my second derivative. And that one is going to be derivative of a half is 0. Derivative of negative cosine x is minus a minus sine x, which is a positive sine x. Okay? So now, what we're going to do, I'm going to erase this stuff just so I have some room to write. We are going to fill in our box here and figure out what our f of c and our f double prime of c are for our 3 critical points. So now, our f of negative 5 pi over 3, we've got 1/2 times negative 5 pi over 3 minus the sine of negative 5 pi over 3. And so this one is going to be negative 5 pi over 6. And this one is going to be minus square root of 3 over 2. And then we have f of negative pi over 3. So 1/2 times negative pi over 3 minus the sine of negative pi over 3. So this is negative pi over 6. Minus a minus would be plus square root of 3 over 2. And then f of pi over 3, 1/2 times pi over 3 minus the sine of pi over 3. Pi over 6. And then minus square root of 3 over 2. So we've got negative 5 pi over 6 minus the square root of 3 over 2. We've got negative pi over 6 plus the square root of 3 over 2. And we've got pi over 6 minus the square root of 3 over 2. And now we want to look at what is happening with the second derivative at these points. And we just need to know positives or negatives. So basically, the sine of negative 5 pi over 3 is positive. Because remember, negative 5 pi over 3 is in the first quadrant. Sine's positive in the first quadrant. Sine of negative pi over 3, that one's going to be negative. That's in the fourth quadrant. And sine is negative in the fourth quadrant. Sine of positive pi over 3 is going to be positive. Because we really don't need to know the value. We just need to know whether it's positive or negative. If it's positive, then we're talking about concave up and we're talking about a minimum, right? So positive tells us we have a minimum and negative tells us we have a maximum. So I'm going to go ahead and put our conclusion over here. This is our conclusion that number 1, we have local mins are, and I went ahead and put those in my calculator and got values. Negative 3.484 at x equals negative 5 pi over 3, and negative 0.342 at x equals pi over 3, and since f double prime of x is greater than 0 and f is concave up. So therefore we had minimums there. And the second thing that we see, local max value is about 0.342. Sorry, my about looks like it's a negative. At x equals negative pi over 3, since f double prime of x is less than 0 and f is concave down. So concave down gives you that maximum. And that is our finding the max and the min using the second derivative test. Normally, when you're doing this, you would not have your first derivative. They would only give you values for your second derivative, and they would give you the critical points. But so some people say, well, why would you use the second derivative test if you you could just use the first derivative test? Well, they like to give it to you where you have to use it because they don't give you the other stuff to be able to use the first derivative test. Anyway, it's hard to explain, but that's usually on the AP exam. All right, so example number 8, the graph of f prime, the derivative of a function f is shown. On what open interval is f increasing? So if we want to know where f is increasing, we're going to look to see where f prime is positive. So you can see here where f prime is positive. So we're going to say that f increases where f prime of x is greater than 0. And this occurs on negative infinity to a and b to c. At what values of x does f have a local maximum or a local minimum? So if this is the derivative, remember your zeros for your derivative. So your critical points would have been found by setting your derivative equal to 0, and the critical points would have been x equals a, x equals b, and x equals c. And you can see that if you then made a sign chart, A, B, C, and you were looking at f prime, it would be positive, negative, positive, negative. And so you can see from positive to negative, this one's going to be a max. Negative to positive, this one's going to be a min. Positive to negative, this one's going to be a max. Okay, because we're using f prime to tell us things about f, and they're asking where does f have a local max or a local min. So now we're going to say f has a local max at x equals a and x equals c, because f prime of x changes from positive to negative at x equals a and x equals c. And then we'll say f has a local minimum at x equals b, because f prime of x changes from negative to positive at x equals b. Okay? And then state the inflection point of f and justify. Well, to state the inflection point, what would you have to know? We'd have to think about, and I'm going to do it in blue, we have negative, 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 negative slopes of tangent lines, then we would have 0. So we would come up here, if I was going to draw the graph of the derivative, I would put a 0 there, and I know that my second derivative is coming up like that. Then we would have positive, 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 and then 0. So I know I have another 0 here, and it would be positive, 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 and then go to 0, and then negative, 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 negative on after that. So I have just drawn the f double prime, and so inflection point possibilities are where your second derivative is 0. So if we looked at the point, this is at -1 and at 3, and we look and we say, oh, well, our second derivative is negative to positive to negative. And so you can see that when it changes like that, that these are both going to be points of inflection. And so we're going to say f has points of inflection at x equals -1 and x equals 3 because f double prime of x equals 0 here, and f double prime of x changes sign at each of these points. Because it's not enough just to be 0 there. They have to change signs. If they went from negative to negative or positive to positive, they would not be considered points of inflection. All right, so on what interval is the function f concave up and concave down? So we can see that by looking right here at this second derivative sign chart, but a sign chart is not enough to say, oh, look at that sign chart. You have to explain it. So we're going to say that f is concave up on -1, 3, since f double prime is greater than 0, f double prime of x, I guess I would say, is greater than 0, on that interval. And then I would say, I'm going to put the rest of it, I guess, right here. F is concave down on -infinity to -1 union 3 to infinity, because f double prime of x is less than 0 for those intervals. Okay, so those are our two answers for that part D. Okay, you had to talk about where is it concave up, and you had to justify, and where is it concave down, and you had to justify. Part E, it says, assume that f of 0 is 0. Can you sketch a graph of f of x? So we know a lot about what's going on. We know that we have these critical points where A is a max, B is a min, and C is a max. It looks like it's a quartic function because if I started out with a quartic function, my first derivative would have been cubic and my second derivative would have been quadratic. So I do think it's going to be some sort of quartic function. I also know that where it's concave up and where it's concave down and where its points of inflection are. So once you know that stuff, you can kind of start trying to sketch a graph. So what I did was I kind of said, okay, well, here's my A, here's my -1. It told us that f of 0 was 0, so I'm going to put that point in there. I'm going to put in a B, I'm going to put in a 3, and I'm going to put in a C. Okay? So I put a maximum at A, and then I come down, oops. Having trouble writing with this, I'm so sorry. Maximum at A, and I come down and I try to make my -1 my point of inflection. Where it goes from being concave down, I'm going to start it being concave up. So at this point, do you see how it has to be kind of midway from being concave down to concave up? At B, I have a minimum, so I need to sketch that minimum in there. I've got a point of inflection at 3 where it goes from being concave up. So here at C, I have a maximum again. I want it to go concave down. So I think that that is about what my function would look like, and it is, it does look like a quartic function, with lead coefficient that's negative. Okay, so example number 9. In the table at the right, selected values for g of x, g prime of x, and g double prime of x are shown. The function y equals g of x is a twice differentiable function and continuous on the closed interval from -4 to 5. Explain why there must be a value x equals c on -4, 5 such that g of c is 7. So what we're going to look at is we're going to look at what is happening at the endpoints, right? So we're going to say g of -4, and if we look, we see it's 0. And then we're going to look at g of 5. And if we look at that, we see 8. And we say, since 7 is between 0 and 8, and g is continuous on the closed interval -4, 5, and differentiable, actually, we don't have to talk about differentiable yet, so sorry, but we're just going to say, since it is continuous, because all they're asking here is there a value that's 7? Sorry. They haven't said anything about, average value or anything like that. So since 7 is between 0 and 8 and g is continuous on -4, 5, by the intermediate value theorem, IVT, there must be a value x equals c on -4, 5 where g of c is 7. Okay, so they're just basically saying, hey, if it's going to go through 0, if it's going to go from 0 to 8 and it's continuous, then therefore somewhere it had to have been 7. Explain why there must be a value of x equals d on -4, 5 such that g prime of d is 8/9. Okay, now we want to talk about the mean value theorem. So, we're going to calculate g of 5 minus g of -4 divided by 5 minus a -4. Okay, that is our average rate of change from one endpoint to the other endpoint, from -4 to 5. That would be the slope of our secant line. And so when we do this, we get 8 minus 0 over 9. We get 8/9, okay? So now we're going to say, since g is continuous on the closed interval -4, 5 and differentiable on the open interval -4, 5 by the intermediate value theorem, by the mean value theorem, there is at least one value such that such that g prime of d is 8/9, and d has to be in -4, 5. Okay, right? One value d in -4, 5 such that g prime of d is 8/9. Because remember what the mean value theorem says, if I've got some function from, -4 to 5, and I say, okay, well, here's my slope of my secant, what the mean value theorem is saying is, if it's continuous and differentiable, there's going to be some equation of the tangent line that's parallel to that, so that the slopes would be the same. Okay, and then part C, does g of x have a local maximum, local minimum, or neither at x equals 3 and justify? So we're going to be looking at g prime of 3. And if I go to the chart, my g prime of 3 is 0.
I'm so hungry.
Honey, I'm doing a video, which is a critical number. So when you have a derivative that's 0, that's going to be a critical number. And if we look at g double prime at 3, if we look over there, g double prime of 3, I just wrote 4, sorry, it's -2. Glad I caught it, and glad I caught that. G double prime of 3 is negative. Okay, so that means it is concave down, right? So that means that we have a local maximum by the second derivative test. So we say, I'm going to put it over here. We say, so g of x is concave down at x equals 3. Thus, g of 3 equals 4 is a local maximum by the second derivative test. And then part D, can concavity of g of x be determined on the interval from -4 to 5? Why or why not? Now think about what you have to know about concavity. You have to know your critical points for your second derivative, and they really haven't given us our critical points for our second derivative. So there's not going to be enough information to determine concavity because we only have also the endpoints and x equals 3. So infinitely many points are missing to establish concavity. So let's write that somehow. We're going to say no. There is not enough information to determine concavity on -4, 5. We only have endpoints and x equals 3. So infinitely many points are missing to establish concavity. Okay, so here is the summary of our first and second derivative tests. And you can see that if you've got a positive first derivative, it's increasing, positive second derivative, concave up. If we have a positive first derivative increasing and a negative second derivative, concave down. Positive first derivative and a 0 second derivative, you have increasing and an inflection point. Negative first derivative, decreasing, positive second derivative, concave down. This is supposed to say up, sorry. Positive second derivative, that should have been up. So decreasing and concave up, sorry about that. Negative first derivative is decreasing, negative second derivative, concave down. Negative first derivative, decreasing, second derivative of 0 is an inflection point. If our first derivative is 0 and our second derivative is positive, we have a relative min because it's concave up. If your first derivative is 0 and your second derivative is negative, you have a relative max because the function is concave down. And then if you have first derivative 0 and second derivative 0, the function is smooth, level, and a possible inflection point. All right, we finally got through our